Lessons on lessons on lessons.
Hi guys, I'm Parth.
I'm Kendra.
I'm Akash.
I'm Nikita.
And today we'll be talking about rational functions. Before we begin, we should know what a rational function is.
A rational function, f of x, is the quotient of two polynomial functions, a of x and b of x. So basically there's one polynomial on top of another.
And where b of x cannot equal 0. Alright, now that we have defined a rational function, we can now look at what a rational function looks like. The parent function is f of x equals 1 over x, where we have two asymptotes. One, x equals 0, and another, y equals 0.
You also have a horizontal asymptote, but we'll get into why in a bit.
In order to graph a rational function, we must know the components of a function. This includes the x and y intercepts, the symmetry, any possible holes, and the asymptotes.
You can't touch this. You can't touch this.
Now we'll talk about the x and y intercepts. To find the x-intercept, you must substitute 0 in for y and solve the resulting equation. This is because the x-intercept has an order pair of x, 0. So since we know that y is 0, we substitute it in for f of x in the equation, which is the y output. So in this example, we set the equation equivalent to 0, and we solve for x equals -1. Thus, the x-intercept is -1, 0. Similarly, to find the y-intercept, you must substitute 0 in for x and solve the resulting equation. This is because the y-intercept has an order pair of 0, y. In this example, we substitute 0 in for x and we get -1/2, so the y-intercept is 0, -1/2.
So now we're going to talk about symmetry. So basically, symmetry is a key component to graphing because it can save you time if you know how the graph will look. Y-axis symmetry is a symmetry across the y-axis. So if you substitute in a -x where x is, then the result should be the same. So in our example, we have f of x equals x squared plus 1 over x squared plus 2. So if you plug in a -x in, the answer, the function won't change because it's the second power. And then origin symmetry can be found by substituting in a -y for y and a -x for x. And the resulting function should be the same as the original function. So we have f of x equals 1 over x, and then if you make the y negative and the x negative, the answer is still the same as the original function.
Now that we've talked about symmetry, we're going to talk about holes and vertical asymptotes. You can find a hole by factoring the polynomials in the numerator and in the denominator. If you see the same factor in both, in this case x plus 3, you cancel them out. Use a simplified function for your vertical asymptote. So in this case, it'd be 1 over x plus 1, and the vertical asymptote would be x equals -1. You take the x value of the factor that was canceled out and substitute it in a simplified function, which is 1 over x plus 1, to get the whole -3 and -1/2. Back to asymptotes, starting with the vertical asymptote. There are values that cannot be a part of the graph and they will result in the denominator of 0.
Now that we're done talking about horizontal asymptotes, we can now talk about end behavior asymptotes. These asymptotes will be horizontal or oblique, depending on the degree of the numerator and the denominator and how they compare. In the first instance, the degrees of the numerator and the denominator are going to be equal. In this case, we will find the leading coefficient of both the numerator and the denominator. And this ratio will be your horizontal asymptote. In this scenario, we have x squared plus 3 over 3x squared minus 1. Both the numerator and the denominator have a degree of 2. So we found the ratio and it was 1/3. Our horizontal asymptote will be at y equals 1/3.
Another instance of the end behavior asymptote is when the degree of the numerator is less than the degree of the denominator. So in our example, we have x plus 3 over 3x squared minus 1. So since the degree in the denominator is 2 and the degree in the numerator is 1, your asymptote will always be at y equals 0.
The final instance we'll be talking about when it comes to end behavior asymptotes will be in the instance where the degree of the numerator is greater than the degree of the denominator. When this happens, you're not going to get a horizontal asymptote. Instead, you're going to be getting an oblique asymptote. And right now for you guys will be focusing on slant asymptotes, where the equation of the asymptote will be a line. So, for our example, 2x raised to the third over x squared plus x minus 12. Clearly, the degree of the numerator is greater than the degree of the denominator. So we have no horizontal asymptote. In order to find the equation of the slant asymptote, we'll be doing polynomial division, long division. And when we do this, we'll find the quotient to be 2x minus 2. This will be the equation of our slant asymptote. When we're dealing with end behavior asymptotes, it is possible for the graph to cross the asymptotes. However, keep in mind that this is not true for vertical asymptotes. In order to find the crossing point, you take the remainder of the long division and set it equal to 0. When you find the result, that will be your x-coordinate. To find the y-coordinate, you simply you substitute 12 over 13 into the slant to find your y-coordinate. Okay guys, now that we've finished talking about the components of a rational function, we can finally graph one. So, in our example, we have x plus 3 over x squared plus 4x plus 3. We simplified this down to get x plus 3 over x plus 3 multiplied by the quantity of x plus 1. Obviously, x plus 3, we can cancel those out. We're left with 1 over x plus 1. We started off by finding the x-intercept. We substituted 0 in for f of x, and we found that we have no x-intercept. Next, for our y-intercept, we substituted 0 in for x, found that we have a y-intercept at 0, 1. So, here we go, pull that in. Now, our horizontal asymptote. We looked at the numerator and the denominator, the 2 degrees. We know saying 1 is the same thing as saying x to the 0th power. And now we have a degree of 1 here. So clearly the degree of the denominator is greater. So we have a horizontal asymptote at y equals 0. Now, with our vertical asymptote, we look to the denominator. X can't be negative 1, or we're going to have 0 in the denominator, or an undefined function. So now, that led us to find the vertical asymptote to be x equals negative 1. Now, when we canceled out x plus 3, we realized that there has to be a hole at negative 3. To find the y-coordinate, we substituted negative 3 in for x over here, and found that y is going to be negative 1/2. There are no crossing points in this, because we are not dealing with any oblique asymptotes, and the horizontal asymptote will not be crossed. Symmetry, we found that there was no y-axis symmetry when we substituted negative x in, and there was also no origin symmetry when we substituted negative y and negative x. So now we're ready to graph. We have our y-intercept over here, and since we have these two asymptotes, your graph will approach both asymptotes. So here's what it'll look like. Remember to label your asymptotes with dashed lines so they don't get confused with the solid line of your graph. Down here, to label the hole, is simply an open circle. So here it is at negative 3 1/2. And the graph will approach both asymptotes. We understand that we don't know the definite point over here at this vertex, but it's not important for now, and you'll probably learn that in a couple years. But for now, we just need to get the basic sketch of the graph. So yeah, after we found the intercepts, we found the asymptotes, we checked for holes, we checked for crossing point, we checked for symmetry, and we were able to graph this function. Alright guys, now that we've finished our first example, we can move on to our second. We have 2 multiplied by x to the x cubed over x squared plus x minus 12. I simply factored the denominator to get x plus 4 multiplied by the quantity of x minus 3. Our intercepts, substituted to find the x-intercept, I substituted 0 in for f of x, solved, and got 0, 0. And if you know the origin is our x-intercept, it's also our y-intercept. Before I get into end behavior asymptotes, found the vertical asymptote. Pretty simple. X can't be -4, x can't be 3, but we're going to have a denominator of 0. So these are our asymptotes. So I drew them in. -4 and 3. Symmetry. We found that there was no y-axis symmetry and there was no origin symmetry. But I'd like to explain why these would be useful if there was either one. For y-axis symmetry, if you knew x, then you also knew -x, and you would know what -x is, and vice versa. So, and for origin, if you knew what x, y was, you would also know what -x and -y were. So, just keep that in mind whenever you see symmetry. Moving on, found our end behavior asymptotes. Since the degree of the numerator was 3 and the degree of the denominator was 2, the degree of the numerator was obviously 1 greater, so we know we're dealing with an oblique, and more specifically a slant asymptote. So, we did our polynomial long division. Our quotient came out to 2x minus 2. That's the equation of our asymptote. I drew that in. And to find the crossing point, we took the remainder and set it equal to 0. The x-coordinate we found was 12, 13. And in order to find the y-coordinate, we simply substituted it back into the equation of the line. And we got -2, 13. So we know our crossing point is at 12, 13 and -2, 13. So right about here. So, now that we have our asymptotes, we have our intercepts, we can now graph. So I put in our slant asymptote, our vertical asymptote, we know our intercept, and now since we know the intercept and the asymptote, there's a problem. We don't know which way the graph is going to go. So when you're in this instance, you should take points, x points, choose smart points. I took one to the left of the intercept and one to the right of the intercept. So I found -39 was a point, all the way up here. And then -2.67 was another point, so it's right about here. So there you go. So what we have here is basically a cubic function. It looks like a cubic function. And just drew that in. Right there. And now notice, we still have these parts of the graph. And we don't know exactly where the vertex is going to be. But we know that the graph will approach both asymptotes. So I just simply drew in this figure right here. These two. Because keep in mind, a graph has to be everywhere where the asymptotes are not. So make sure you do that. And with that, you've learned how to graph and analyze rational functions. This will be especially important in later classes. And with that, we thank you for watching, and we wish you best of luck in Algebra 2. Thank you.
That's how I'm supposed to be. Yeah, that's how I'm supposed to be. Yeah, that's how I'm supposed to be. Everything look like a post.